So I want to take this logistic growth model, this equation, and see what it would look like if we apply it to a real life situation with a real population. So I've done that. I've programmed here a Microsoft Excel file that will show us what's going on with the population over time. All right, so if we look here, I've got all the components of the equation. All right, so time, so 1 year, 2 year, 3, 4, 5, up to 25 years. The value for R, so that instantaneous growth rate, and then the value for the current population size and the carrying capacity. And I've started out here with just kind of a standard population. So we imagine we start out our populations at 10 individuals, and then carrying capacity of 500, and then it gets larger and larger and larger and larger. And then at some point that growth rate starts to slow down as it approaches the carrying capacity of 500, 499 being the highest number that we've reached on this example. Right, so now I want to think about what would happen in this population if we adjust that value for R, for that growth rate. So let's say we go from 0.4 to 0.6. What we should see is that the curve is similar, but goes up a little faster. Right? So it gets up to carrying capacity sooner with a higher growth rate. We go up to 0.8, it gets up there even faster. We go to 0.9, even faster. We go up to 1, even faster. If we go to 1.3, even faster. If we go to 1.5, oh, look at what's happened here. So something interesting. So our population has been growing quite rapidly, and then we get up here and the population has actually gone past the carrying capacity. So this is an important point. It is possible for the logistic growth model for a population to go past the carrying capacity. And when it does, well, then we end up with a negative growth rate, right? The population gets pushed back down to the carrying capacity, right? So it goes up above it. In fact, if we go up a little higher, let's do 1.7. Oh yeah, so here population grows much higher, and then gets pushed back down, and then overshoots it again, and then back down, and eventually settles down onto the carrying capacity. Some interesting things start to happen as we get higher and higher growth rates. Let me go up here to 1.9. Let's do 2. Oh, so 2, so this is interesting. If we look and see what happens here, the population is going above carrying capacity, then below, then above, then below, then above, then below, then above, then below. That it's oscillating back and forth. It's never actually at carrying capacity, right? But it's shooting past it and then dropping back below it and then shooting past and back below. And this is mathematically at least a stable oscillation. It's going to never actually be at carrying capacity, but it's going to oscillate above and below it. All right, so let's go a little higher. Okay, so this is an interesting one. Take a look at this for a second and contemplate what's going to happen to this population. This population is going extinct because it's getting larger and larger amplitude of that oscillation, right? The bigger this gets, at some point, it's going to go all the way down to 0. And as soon as it goes down to 0, the population's extinct, right? So let's apply this to the real world, right? Let's imagine that you're not keeping a very careful track of your population. You go out occasionally and do some surveys, and you say, oh yeah, no problem. It's around 500, anywhere between 440 and 550. Population's doing fine. When in reality, if this is not addressed, this population is going to go extinct, right? If you had the details and you could see this, you can see that danger of your population. Let's go even higher. So 2.3, really big oscillations. 2.5, even bigger oscillations. 2.7. Again, this would be a population to be really concerned about just because it's so unpredictable. It's kind of all over the place. We'll try 2.9, really all over the place, really dangerous. 3, oh, look at that. Mathematically, we can still do some stuff, but right here went extinct. In the 8th year, population went to 0, and so at this point, nothing else could have happened. We can still, again, mathematically do some calculations, but extinction. Oh, yep, extinct. We're up to 4. Oh, extinct really fast. So, here's my point. When we're thinking about actual populations, if we get above the carrying capacity, growth rate is going to be negative, it's going to push it back toward carrying capacity. But if we get really high values for R, things become unpredictable. Things become all over the place to the point of extinction. And so, if we are a manager of a wildlife population and we're concerned about it remaining stable, we need to know these things about those fluctuations. We've actually seen this sort of thing happen in the past. We'll talk about this in more detail later on in the course, but we've seen this sort of thing happen. Something that's relatively common is a new species will get introduced to an area. It'll become really common, it'll grow really fast, and then it'll crash, it'll disappear. Why? Well, maybe it so far exceeded carrying capacity that the negative growth in the next year will push it so far down that it was gone. Right? So, yes, this is just an equation for us to keep track of that, but we can apply this to real populations and see how it affects those real populations. And yes, real populations will definitely exceed carrying capacity at times. Right? Anytime we get a value for n that's greater than k, we're over the carrying capacity. That's going to make this value greater than 1. That's going to make this whole thing negative. A negative growth rate, population getting smaller. All right, so let's apply this to a real population, the human population. All right, so people have known about this idea for carrying capacity for a long time, contemplating how many individuals can be supported. And in 1920, some population biologists looked at the human population and made some predictions. All right, so 1920, human population has been growing. It's about to this point that we see on the graph, the United States population. And then predictions are made that the carrying capacity for the United States is around 200 million individuals. All right, so let's see what happens. Current U.S. population, 300 million. So we have to ask the question, well, why? Why is it if the estimated carrying capacity was around 200 million, have we been able to exceed that carrying capacity and continue to have pretty dramatic growth of our population, even though it was estimated that there wouldn't be enough resources to support that many people? Well, there's a few different reasons. One is, technologically, we got a lot better at stuff. We got a lot better, for example, at agriculture. We can produce a lot more food now than we could in 1920. It's because of better crops that have been improved through artificial selection and through genetic modification, through the technology of having better equipment that can more efficiently plant and harvest crops, the use of things like pesticides and herbicides and fertilizers that help us grow more food. All those things added together means we can produce more food than we did back then. Additionally, transportation has become better, so we can also import food, right? One of the things that you might notice if you go to the grocery store is a lot of the foods that are there are not from the United States. And so more food available means we can support more people. We have also increased the chances of people surviving. So one thing that's happened is medicine has gotten a lot better. The chances of dying have gone down. We also have a lot of immigration happening. Now, one of the reasons that immigration can help avoid that carrying capacity prediction is that immigrants are at least partially resourced somewhere else, right? During that time period where you're growing and consuming a lot of food, well, maybe you grew up somewhere else and then you come to the United States, right? So you put all this together, and what do you get? You get a possibility that we are supporting way more people than it was predicted. Now, don't forget, there is always going to be a limit, right? You can't have growth forever, but currently the population continues to increase past current prediction or past previous predictions to, well, we don't know how high it will go. All right, the next thing I want to think about is how we've generally been thinking so far about the population overall, right? Kind of the big picture, we say, oh, the human population is over 300 million. We haven't thought too much about, well, who those individuals are, how those individuals may differ from each other, and not everybody is exactly the same. Well, it turns out that if we start looking within a population, those values of R and lambda may not really take into account the variation, and sometimes the very important variation that we find within that population. That we know that individuals are going to vary with things like their chances of surviving, things like how well they reproduce. For example, I have some pictures on the screen here. All three of these pictures are marbled salamanders. On the far left, we have marbled salamanders in the egg form. In the middle, we have a larval marbled salamander. And then on the far right there, we have an adult marbled salamander. And so if we just say we have a population of 100 marbled salamanders, well, it's going to matter to us, right? Whether those hundreds are adults that are ready to reproduce, or whether those 100 are eggs or larvae that they're going to survive and reproduce differently, depending on what our population is actually like. And so when we think about a population, we can divide it up into different ages, different sizes, male versus female, reproductive classes. So in this case, we have an egg form versus a larval form versus an adult form, right? That all those things are going to matter within our population. Now, one of the ways that we see populations vary is in how well they survive. So we're going to call these survivorship curves. And we're going to say, okay, if we look within our population, when is it most likely for individuals to die? In other words, if we have our sort of lifespan on the x-axis there, when is most mortality occurring? When are most of them dying? We as humans are used to our type 1 survivorship curve. Something like a grizzly bear would also follow that survivorship curve, where there's not a whole lot of mortality early and where most of the death comes from old age, right? That most death is sort of concentrated towards the end of that lifespan. Not all species have that sort of survivorship curve, though. For example, if we think about something like a plant, the example that on the diagram here is the dandelion. Dandelions produce many seeds. And many of those seeds are not going to make it. They're going to land in inhospitable areas. They're not going to grow. Even the ones who land in appropriate areas, as they start to grow, many of them are not going to survive, right? A rabbit's going to come along and eat them when they're still in their earliest stages, and they don't have enough resources left over, and they don't make it. And so in a type 3 survivorship curve, we have a lot of mortality early in life, and then later on, it kind of levels off. Another example, this one might be fish. Fish lay, in some cases, hundreds of thousands or millions of eggs. The vast majority of those eggs don't make it. And so, as those eggs are not surviving, the mortality is very high early on. And even young fish, right? When you're a little tiny fish that's half an inch long or an inch long, who eats you? Everything. But at some point, right, that little fish is going to grow up to be big enough that it's going to be less likely to be eaten. And so at some point, as it gets a little older, the chances of dying are going to drop dramatically. And then at some point, it's maybe going to be so large that nobody eats it, right? So that sort of life cycle would have this very strong mortality early on and then kind of level off. Now, right in the middle, the least common of the three is probably the type 2 survivorship curve. And in a type 2 curve, mortality is about equally likely throughout its entire life. And so the example on the diagram there is a squirrel. Think about what kills squirrels. Well, hawks and cars. The suggestion here is that a squirrel is probably just as likely to get eaten by a hawk or run over by a car at any point during its life. And so there's no real times of more or less mortality. It's kind of just a equal chance throughout the life cycle. All right, now, a couple important things to notice here. Type 1 survivorship curves tend to belong to organisms with larger body sizes. So humans, grizzly bears, whales, right, have a few offspring, invest a lot into them. Those offspring have a pretty good chance of making it. And then there's very little chance of them dying until they get to be very old, and old age kills them. Type 3 survivorship curves often are found with smaller body-sized organisms, not exclusively, but often smaller things have lots of mortality early. And then that mortality kind of levels off later on. Type 2, a little less predictable. Maybe you could say intermediate, but I wouldn't make any generalizations there. Now, here's also something important to point out. The survivorship curve that a species has is not necessarily set in stone. It can change. If a population experiences a really bad disease, for example, maybe the survivorship curve changes. Or if there's a lot of competition and resources are really limited, maybe there's a natural disaster and a lot of resources are not available when they were before, that survivorship curve can change, right? So it's not necessarily always going to be this. It's what is happening most of the time, but conditions can change and survivorship can change. Something else to think about is that you can see over here on the far left of the type 1 and type 2, there's some kind of steep drops early on. Well, that's because when organisms are very, very young, even if they have a type 1 survivorship curve, there's still a decent chance of them dying. And so they're very vulnerable when they're first born, and so we got a little bit of that type 3 curve in a type 1 and a type 2 curve. And additionally, old age is dangerous for anybody, no matter whether they have a type 1, type 2, or type 3 curve. So most survivorship curves incorporate some parts of a type 1 and a type 3. Even if overall it's a different curve, there's a little bit of that that's going to be going on. And that can be increased, right, if conditions change. You can have more of that type 3 curve, for example, if it's a really rough year, perhaps. All right, so let's keep thinking about population variation. And I want to think about the variation of a population due to the age structure. So, for example, here is the age structure of the United States. So what we see here is the x-axis is number of individuals in millions. Y-axis are these 5-year age classes. Right? So youngest age at the bottom, oldest age is up here at the top. If we take a look at the United States age structure, we see that, well, the sides are pretty vertical. We got a little bit of a bulge here. What's that? Well, those are the baby boomers. But overall, everything is relatively equal. What that means is the population of the United States is probably not increasing or decreasing too much. It's probably staying relatively consistent. Let's compare that to someplace like India. So in this example, we see that we're very much biased towards the younger age classes. The reproductive ages, and especially pre-reproductive ages, are much, much, much more numerous than the older age classes. What that means is that this population is growing, that those individuals that are going to become reproductive soon are a great percentage of the population. So this population is going to be getting larger and larger in the future. Third possibility. Well, in the third possibility, we have a population where there's more older people than younger people, that the reproductive and the pre-reproductive age classes look to be the smallest, meaning that this population is going to be decreasing. The size of the population is getting smaller over time, right? So even if, and this isn't the case, but let's just imagine, even if all three of these populations were identical, they all had exactly the same number of individuals, that's a very different outcome for the population. The United States population is staying the same size, the Indian population increasing dramatically, and the Germany population decreasing. So it's not just the number of individuals who's in the population, it's also what ages those individuals are. Let's look at another example here of a way that we could think about population. And we're going to look at something called a cohort life table. And a cohort life table is basically keeping track of a single cohort. A cohort is just a group of individuals that are sort of in the same group. We often talk about the freshman cohort in college, right? The people who started school at the same time. And so here we're looking at a single cohort. In this case, we're going to look at a single year in the life of a species, and we're going to say that this is an annual species, a species that only lives for a single year. We're going to keep track of what's going on in that population. Some ways that we can calculate some things about that population and how it's changing and what's happening with it over the course of that year that it's alive. So what we have here then, the age column is referring to months old. So 0 months old, so just born, 1 month old, 2 months old, 3 months old, 4 months old. We're imagining something like an annual plant. An annual plant is going to start growing in the spring, so 0 month old, and then it's going to grow over the course of the summer, and then it's going to not survive the entire summer. So we see that our number alive, while we started with 500 individuals, by the time we get to the end of the summer, right, to this 4th month, we have 0 individuals left. So our cohort life table is keeping track of those individuals over time. Now, one of the things that we can keep track of here is the survival rate. And the survival rate says, if you are alive at the beginning of a time period, what are the chances you're still alive at the beginning of the next time period? All right, so for example, for this age 0 month, we start out with 500 individuals, and at the beginning of 1 month, 400 individuals are still alive. So 400 out of 500, there's an 80% survival rate. If we look at the next time period, we start out with 400, we end up with 200, so there's only a 50% survival rate. Again, 50% for the 2-month age class, we start out with 200, we end up with 100 in the 3rd month. And so we can just do those calculations real quickly, and we can see the sort of the chances of surviving from the beginning of the time period to the beginning of the next time period. Since all the individuals are dead at the beginning of the 4th month, this last survival rate here is 0. All right, so take a look at those, make sure you see where those come from. 400 out of 500 is 80%, 200 out of 400 is 50%, 100 out of 200 is 50%, 0 out of 100 is 0. Now, we could also look at survivorship. Survivorship is saying, what are the chances of surviving to this time class, right? So overall. So, for example, we have 500 individuals alive at the beginning. The survivorship for that first time class then would be, if you're alive at the beginning, what are your chances you're alive at the beginning? Well, the answer is 100%. If you're alive at the beginning, what are your chances that you're alive at the beginning of 1 month? 400 to 500, 80%. If you're alive at the beginning, what are the chances that you're alive at the beginning of 2 months? Well, that's going to be just 200 divided by 500. That's going to be 40%. Right? In other words, if you're alive at the beginning, there's a 40% chance that you're going to make it to that 2-month time class. And then 1 out of 5, a 20% chance that you're going to make it to the 3rd time class. And a 0% chance you're going to make it to the 4th. All right, so survivorship is from the beginning, whereas survival rate is from the beginning of the previous time period to the next time period. Okay. We've been keeping track of the number of individuals alive, and we've just done some calculations based on how many are surviving for how long. We're now going to bring reproduction into this. So our next column, B sub x, is average number of offspring produced per individual. So for our purposes, let's imagine that the 0-month and the 1-month-old individuals are not old enough to reproduce yet, but the 2- and 3-month-old are. And so the average number of offspring produced per individual is 1/4 for the 2-month time class and 4 for the 3-month time class. Using that information, we can then calculate Lx times Bx. So Lx is that survivorship column, Bx is the reproduction column. This calculation is basically saying, what are the chances you'll still be alive at each time class? And if you are, how much reproduction are you doing? So, Lx times Bx, so 0.4 times 0.25 will be 0.1. And then 0.2 times 4 is 0.8. Lx times Bx. All right. Using that information, we can calculate something then called the net reproductive rate. We're going to use capital R for this. And the net reproductive rate is just going to be adding up all the values for Lx times Bx. So in our example here, we got 0.1 plus 0.8 equals 0.9. Now, here's why we're interested in this. Here's how we're going to use this. What that's saying is that if we start out with 100% of the population, the reproductive rate of this entire population is only replacing 90%. That if we start out with 500 individuals, we are only producing 500 times 0.9, which is 450 individuals. So because our net reproductive rate is less than 1, we're saying that this population is getting smaller. That there were 500 seeds that started growing at the beginning of this cohort. Next year's cohort is only going to have 450. A net reproductive rate less than 1, population is going to be getting smaller. Now, I will also point out there's another way to calculate this, and that's just by looking at the number of individuals and how much reproduction they're doing. And so the 2-month time class, we have 200 individuals. Average number of offspring produced is 1/4, so 200 times 1/4 is 50. The 3-month time class, 100 individuals, each producing 4. So 100 times 4 is 400. So 400 plus 50 is 450. 450 divided by 500 is 0.9. Right? They both are saying exactly the same thing. It's just a way to keep track of what's going on in our population. Now, you might be thinking, who cares? This is just a bunch of numbers. Does it mean anything? I don't care about this. This is stupid. How did I get involved in this? This was a mistake taking this class. Okay, you might be thinking that, but I want to see how we could actually use this. So let's imagine that you were the person who's involved with managing a species, perhaps it's endangered. And you're looking at your individuals in this endangered wildflower species, and you say, uh-oh, net reproductive rate 0.9. That means my population of these endangered wildflowers are getting smaller. I got to do something to fix it. If you have this cohort life table, right, if you can keep track of what's going on, then you can see where it would really matter to try to help them. And so you say, okay, my population's doing really poorly. I need to get more for next year. You say, you know what? The net reproductive rate, right, it's really being driven largely by the reproduction during the 3-month time class. If I could get more individuals to survive to 3 months old, I'd have a lot more offspring for next year's population. That really, this appears to be the key age class that has the biggest effect on this population. Yeah, some reproduce when they're 2 months old, but boy, if I could just have twice as many reproducing at the 3-month time class, I'd have a population that's growing instead of getting smaller. Right? It allows us to see those details instead of just using lambda or lowercase r and kind of big picture. This allows us to see where things are happening and what's most important.